Hello everyone. The mineral assigned to me during this course is kaolinite, and I will be presenting I tried to make it pretty simple and to finish it within time. Starting off with the introduction, kaolinite is actually an aluminium silicate, generally called classified as Lear phyllosilicates. It is member of the kaolin group with a chemical forms through chemical weathering of the aluminium minerals such as feldspar. The hardness is from 2 to 2.5 with a specific gravity of 2.16 to 2.6. Generally, the color is white, and however, with the addition of the impurities, sometimes the color turns into cream, yellow, and pinkish as well if mineralite clays are added to them. The streak is white and with a dull luster and flexible to inelastic tenacity. The simple picture I have shown here is from a kaolin deposit of the Twix County, Georgia, USA. This is from a Cretaceous age. It was once a very good deposit of the kaolin. Regarding formation of the kaolinite is generally stable under a relatively low temperature and pressure conditions. And below have shown the phase stability diagram for the different minerals wherein kaolinite is a pair, and it seems to be formed under relatively low temperature below 200 degrees Celsius and even sometimes below 100 degrees Celsius as well. Uh, and the environment is the environment wherein kaolinite forms is purely acidic, and this can also be formed by the weathering in the tropical and temperate climates. The overall conditions for kaolinite formations are it must be an acidic environment with the if found in the by the weathering process. A good drainage is required with a low temperature, typically up to the 100 degrees Celsius or even sometimes below than this. Kaolinite generally has very limited compositional variation within it. However, sometimes by addition of the other minerals or impurities, it can lead to variations both in colors and overall compositions as well. And these variations can come from hydrothermal modifications or weathering. Uh, it can add sometimes the hydrothermal modification adds iron oxides to it, or and it can convert into montmorillonite clays as well sometimes. The ideal versus real composition is ideally it is an Al2Si2O5 aluminium silicate. However, with the addition of impurities, it can affect its color and composition. Main factors influencing the variation are impurities, generally color impurity, other minerals which can change its colors, the formation processes. Microscopic studies have shown that there can be variations in composition from kaolinite particle to kaolinite particle, even within a single sample as well sometimes. Most common impurities in the kaolinite can be iron oxides, montmorillonite clays, and depending on the source of formation and the processes, it may contain traces of other minerals as well. Generally forms in high sulfidation epithermal deposits, occurs in these type of deposits in the advanced argillic zones, and it is associated with the minerals like alunite and pyrophyllite. The two examples I have shared here are Yanacocha from Peru and Pascolama, Chile, Argentina. In supergene environment, It forms through the acid leaching of the rocks above the porphyry copper systems. And the most common acid leaching rocks are potassium and sodiums. In sedimentary environments, it forms laterites and bauxites in the weathering profiles. It has a it is very important mineral in the exploration stage because it is a good indicator of the fluid chemistry. It shows the acid sulfates, the low pH conditions. It also helps us in defining the alteration halos around the ore bodies. Kaolinite is a very good tool for vectoring towards the high sulfidation mineralization centers, and it can also be associated with metals leaching and remobilization. Kaolinite can be detected in modern days, via Aster remote sensing. Especially the band ratio 4 or 5 is sensitive to the kaolinite formation, and it makes it very useful for regional exploration. Other methods includes are the XRD, X-ray diffractions, which can confirm its crystallographic identity, and SEM with microtextual and compositional information can be provided by SEMS or EMPA data as well. In a summary, kaolinite is a key indicator of the acidic hydrothermal fluids. It is very common in the advanced argillic zones in high sulfidation epithermal systems. This can be detected via remote sensing, spectroscopy, and XRD analysis. And finally, it is a very useful tool for targeting the ore zones and also for understanding the fluid evolution. And that's it from my side. I'll be happy to answer if any questions.